Hello everybody, this is Dr. Hassan again in Introduction to Digital System. Okay, we're still working with Boolean algebra, but today the topic of today will be logic function, NAND, NOR, XOR. Okay, so in this topic we're going to discuss the NAND, NOR, XOR and the extension of 3 input gates. Also, how we convert between sum of product and NAND, sum of product to NAND, and NAND to sum of product, and NOR to sum of product to NOR, and NOR to sum of product, and then we talk about positive and negative logic. Now, if we have any logic function of n variables, how many we expected the solution would have? We have formula which say 2 to power 2 to power n. It means if we have two variables, then it will be 2 to power 2 to power 2. It means 16 possibles. Usually we give 4 here, so 2 here, so 14 more are possible to be given. Okay, now you may say, why we consider a new function? I mean, this lead to the new function I would like to discuss in this topic, which is NOR, XOR, and other functions. Why we need this? Because this lead to cheaper hardware and more flexible. Okay, now let me start with the first one, which is NAND gate. We understand AND gate. Okay, just let me take the pen. AND gate here is A, B, multiplication, right? NAND, we added here, you see this circle added here, to say that the output will be reverse. It means I understand from A and B in this truth table, A and B, whenever A and B both are 1, it will be 1. But because of the inverse, all zeros will be 1s, and then a 1 will be 0. So it's like complement of the output of the AND gate. Okay? So NAND gate is the complement of AND gate. Okay? Now from this, several interesting properties given by this gate, which is NAND gate. The first one is NAND A, I mean the input A and A, is AA, right, dash, which means the inverse, right, as we say. But AA, multiply AA, according to the properties of Boolean algebra, can be written as A bar, which is at the end is not. Oh, so from NAND, what we produce is not. If I have A and I want to do not, I can directly use not, or I can use NAND. Okay, now this is first property for NAND gate. The other one is when we have NAND AB. Okay, then NAND AB, it means AB, okay, double bar, which means AB, because the two bars may return to the original state. Oh, this is give me AND. That's great. So from NAND we can come up with AND. Okay, NAND A bar B bar. Okay, it's A bar B bar, all of them bar, another bar, which means by using De Morgan theorem we can have it A plus B. Oh, this is OR. So what does this tell me? This tells me from NAND I can construct not and OR. So NAND give me not and OR. So if I would like to summarize it and put it in between two brackets, I will say any switching function can be constructed with only NAND gate. It's functionally complete because it gives the three functions of AND, OR, NOT. Now NAND gate, as I mentioned the previous discussion, it can be represented here. You can see this is NOT, so AA, it will be in this way, A, right? Bar, which give what? Which give A bar, right? Because I use here De Morgan theorem, and then I get A bar plus A which give me A bar. Okay. And for AND, you can see here A, B, it will be A in this way, B, but bar. If I enter it from here and from here, it will be A, B, bar, dot, A, B, bar, right? Now using the De Morgan theorem, it will give A plus B. By the way, there is another bar here. Okay, forget it. It will be A plus B, which is dot B, which is dot B, because this is AND, dot B, which is AND gate. And for the last one, if we use, by the way, for NOT we use only one NAND. For AND we use two NAND, 1 and 2. And for OR we use 3 NAND, 1, 2, and 3. And you can go through the steps, you will find you come up with the OR results, which at the end A plus B. For NOR gate, sorry, just a minute. For NOR gate, we have the same thing. We also can construct AND, OR, and NOR, okay? OR and NOT. All of them, we can construct them using NOR gate. Okay, as also it is an OR gate, but with a circle at the output, which means the inverse of the output. But the issue here, important to be highlighted, is we can build any IC chip, integrating circuit chip, which will be discussed later in electrical and electronic circuit analysis. We can construct it using NAND and NOR because they are general functions. We can, from NOR or from NAND, we can construct any function we would like. And this, the advantage of this is it's better than you use NAND and NOR than AND and OR, because it's far faster as switching and cheaper in producing or production. NOR gate, you can see here, this is NOT gate, okay? Without this circle, just a minute, without this circle, the output will be A plus A, right? A plus A, but because of the circle, it will be bar. And we know that A plus A is A. So it's A bar, which means it is not gate. Also, from 2 NOR, we can construct OR gate. I advise to go through the steps. It means see the output here and the output here, and check what is the output of this combination. And from 3 NOR gate, we can come up with AND gate. Also, I advise you to go through the steps to see the combination. One more also gate is XOR. XOR. We know OR, okay? We know NOR, NAND and NOR. Now XOR. What is XOR? XOR, X for exclusive. Okay, this is special gate. XOR gate, insert. I will copy from here. XOR gate assert their output when exactly one of the input is assert, hence the name. So you without this simple here to say that this is XOR, okay, and distinguish between the conventional OR and NOR, this is XOR. We understand that for OR, if any one of the variables A and B, any one of them is 1, the output will be 1. Both of them 1, the output will be 1. But in XOR, if and only if any one of them, not both of them, any one of them is 1, the output will be 1. You see here, when B is 1, A is 0, but the output 1. When A is 1, B is 0, the output 1. when A and B both zeros or both ones, the output will be 0. This is called XOR. And simply it can be represented by plus, because at the end, or is a plus, A plus B. Or is represented here by plus inside the circle, to say that 1 and 1 will be 0, but 1 and plus and 0 will be 1. This is XOR. XNOR, okay, the previous one we added here circle, as you can see. The same output, but the complement one. You remember from the previous one? Here and here we have 1, while here and here we have 0. XOR, it means the opposite of this, okay? It means 1 here and 1 here, others are 0. And simply can be presented by circle inside dot, to say that 1.1 is 1, 1.0 is 0. Now let me back to NOR gate equivalence. Now this is NOR, okay? We understand that without the circle, this circle represents the negative. The circle here represents the inverse, okay? So A, B enter to OR gate, it means A here plus B, right? Okay. Now, when it go to the inverse, we have bar across them. Then this means that it get inverted. And simply when we construct the truth table, then A and B, 0, 0, 0, 1, 1, 0, 1, 1, it gives 0 at the beginning and 1s everywhere. The NOR, we will reverse the output, 1 and 0 everywhere, as you can see here. De Morgan is very important theorem actually. It's simplify a lot, and you understand the relationship if A plus B between two brackets, okay, bar, then it can be represented A bar B bar. It's converted from plus into multiply, and also if it is multiply, it's converted into plus. We can use this in simplifying. As example, this expression, I would like to find the complement of this expression. He asked me to, by the way, how to like the question if it is going exam. Complement the expression and simplify. Have a look. Now this bar or this dash, it will be divided, okay, it will be on A multiplied by this expression. So it's multiply, right? And we understand when it is multiply, it's converted into plus. So what I will do, I will say A bar plus the bracket here bar. Now in this bracket here we have B and this expression, so plus, right? So I will use this one. You see here it will convert into multiply. Bar B bar multiply. You see here multiply by this expression bar. Now inside this expression Z dot, right? So multiply. Again, I will use plus. So it will be, you see here, Z plus the bracket bar. Here, it's a plus, right? So what I will use, I will this De Morgan theorem. I always mix between the name. De Moivre theorem in complex number and De Morgan theorem. So try to not to confuse. Okay. So this plus become, you see, multiply. Double bar, it means original A. So you see here, I got it, I simplify it, I use De Morgan theorem. Now example, if you are given, determine the output expression for the below circuit and simplify it using De Morgan theorem. Have a look. This is AND gate and this is NOT gate. NOT gate, we have C here, it will become C dash, right? Agree? Great. This AND gate, no, this is NAND gate. It have three inputs, A, B, and C dash. So I can write A, B, C dash, and because of it is NAND, I will put inverse across it. Agree? You will say it's easy. Okay. Now let me ask a question. This A, B, C dash, between them is point, right? It means dot. It means and. and there is bar here. De Morgan say convert the dot into plus. You see here, plus, it means or. And distribute the bar on A, B, and C dash. It will be A, B, A dash, B dash, plus C dash, double dash. C double dash is C, actually, because it's like the C, and we take the complement, then we took another complement, we back to C. You see how I wrote the final expression by taking them step by step, each input into the final output. Now, universality of NAND and NOR. Have a look here. Have a look here. I will explain it for NAND, and the same thing could be, I mean, you follow the same procedure for NOR. Have a look. Here, A is the input for this NAND, A here and A here. Agree? Okay. So this is NAND, so it will be A dot A with bar. Okay? Now, A dot A with bar, it means at the end, it will be A bar plus A bar, according to whom? De Morgan theorem. But A bar plus A bar equal to A bar. Oh, this is the output. Just a minute. A bar and the input is A. This is definitely not gate or the inverter, as you can see here. It's like the inverter. Now, if I come here, A and B, the output for NAND is AB bar. If it is here, A, B, bar, and here, A, B, bar. When I come to AND, it will be in this way. A, B, bar, between brackets, A, B, bar, but double bar here because it is NAND. Now I can use the Morgan theorem. It will be A bar, you see here, A, B, double bar now, and this multiplication here between two brackets become plus. Okay, A, B, double bar. And this, according to the property of Boolean algebra, is A, B, double bar, which mean it is at the end A, B, because double bar cancel each other, we come up with AB. Oh, this is AND. And the same thing, if we follow the same discussion, we can find the output of this three gates, NAND gates, which give me at the end OR. So this is from where it came, inverter, and OR. The same thing could be discussed here. Follow this, please. You can follow for inverter, for OR, when we have two NOR and three NOR to give AND. So you see, it's full function. NOR and NAND are full function because they give the inverter, the OR, and the AND. You see here, example here. You need to work in this sequence. You see the first one here, as you can see, the first AND gate 1, it means this is the input 1, the input 2, and this is the output of the first AND gate, which is A, B, and here the input number 4, number 5, the steps mean it gives me the output here. Here, as example, I come up with A, B. Here I come up with C, D, and because this is OR, it will give me AB plus CD. Okay? And if I come here, I try to apply it for this. This give me, you see here, this is AND, equivalent to this one, as I mentioned. And this is also AND, equivalent to this one. Please See the output here and here. It's supposed to give AB. And the output here and here. Use paper and pen and try to do it. It should give CD. You got it? And then I use here inverter, NAND, here behave as inverter, and then we come up with the output here and the output here, which give me the NAND here, the output, which is supposed to be the similar to what we got here. Apply the same discussion, but this one. See how it look like the output. These are different examples using NAND and NOR gate. This examples for NAND. Now let me mention to one issue also here related to interpretation of the two NAND gate symbols. Have a look. This is NAND because the circle here. You see AB, usually they are active if they are high. Okay? And because here the circle, which means that this is NAND, the output state should be low. Activate when low state. Now if I use this here, this circle, it means there is inverter at the input. Okay? Whenever there is inverter, then this means activate at low. Okay? Because 0, it will be 1. And here the output is high because there is no inverter. It will be high. The same thing for OR gate. OR gate here, you see the activation will be when it is 1, which is high. And the output high also, because any one of them will be 1, the output will be 1. While here, the inverter, as you can see in the NOR gate and inverter at the input, it's activate at low and output activate also at low. Now if I would like to summarize the discussion, we will say that basic logic function can be made from NAND NOR function. You may ask why? Because it is cheaper and more flexible. Behavior of digital circuit can be represented with waveforms, truth table, or symbols. Primitive gate can be combined to form larger circuits. And Boolean algebra define how binary variables with NAND NOR can be combined. We gave example, we discussed them, and the Morgan theorem or rule is very important when we use the law to simplify the expression to get a more simple expression, and this is reflected on the manufacturing of IC, integrated circuit, and its cost and its flexibility. Let me stop here and see you in the next topic.